Alright, so calculate the pH of a 0.26 molar methylamine solution. I'll give you the formula for methylamine. Okay, you don't have to worry about this. I'll give you the formula. Okay, what you do need to know is the following. If you were to be given this on an exam or a quiz or anything, what is methylamine? Okay, is it a strong acid? It's definitely not a strong acid because it's not one of the six. Is it a weak acid? Okay, the answer is no. Okay, amines are, by giving you the structure, are considered weak bases. Okay, so we must recognize that this is a weak base. Is it a strong base? Absolutely not. What is a strong base? Yes, OH minus is your strong base. So the first and foremost thing, as a class, we must recognize that this is a weak base. Okay, that's number one. Okay, number two, on the exam, quiz, or whatever, wherever, maybe not even in this class, maybe for your, higher level exams, you have to write the equation. Okay, so I'll give you the formula. You need to know that it's a weak base, and weak bases have a Kb. Okay? Weak bases have a Kb. Alright, so the next thing you need to know is that these weak bases will react with water. Okay, this is the Kb. Just like weak acids react with water, and strong acids react with water, and strong bases react with water, okay, this weak base will react with water, and this is something that you should know. Okay? Okay, what do bases do? Okay, bases are going to take the proton. Bases take the proton, so you're left with CH3 NH3 plus. So weak bases react with water to give you what substance? Okay, OH minus. Weak acids react with water to give you what substance? Not OH minus, but H3O plus. Is that what you said? Yes, that's correct. H3O plus. Okay? All right, so this is what we're going to call Kb. Okay, not Ka, this is Kb. Why did I say Kb and not Ka? Because first of all, amines are weak bases. And what do weak bases do? They will react with water to give you OH minus. So this is a source of OH minus. Just like another weak base, ammonia, that you buy from maybe the store, is a source of OH minus because it reacts with water to give you OH minus. So this is a Kb, which is 4.4 times 10 to the minus 4. I'll give you this. Okay, I'll give you that on the exam. You don't need to know it. Okay. So I'll give you the formula. I'll give you the Kb. If it's a weak acid, I will give you the Ka. And you need to come up with this formula. Okay. All right. The question is calculate the pH of 0.26 molar methylamine. All right. So imagine that you have a bottle of methylamine. Here's my bottle of methylamine. Okay. I need to convince you that this bottle of methylamine does not contain methylamine. It does, but it contains other things. What other things does this bottle of methylamine contain? Okay. Obviously, it contains water because water is our solvent. This is all happening dissolved in water. But what else does this contain? What else is in this bottle? Okay, some of this is in the bottle, and some of the OH minus is in the bottle because that methylamine will react with your water. Okay, so we are asked to calculate the pH, and this methylamine, like I said, is not methylamine. There is methylamine, but there's also this thing, methylammonium, CH3NH3 plus, and then there's also OH minus. All right, so because it's a weak base, we'll construct our ice table. Okay, the first and foremost thing, water is a liquid, so we will cross it out. It's not going to be in our ice table. So we have 0.26, okay, initially, and then some of this will react with water. Okay, how much? Some of it will go this way. So this is minus x plus x plus x. Okay. So at equilibrium, which is what E stands for, you get 0.26 minus x plus x and plus x. All right, let's plug this into our equilibrium. All right, so Kb is equal to OH minus times CH3NH3 plus divided by CH3NH2. All right, so let's plug things in. Kb is 4.4 times 10 to the minus 4. Okay, what is OH minus at equilibrium? X. What is CH3NH3 plus at equilibrium? X. What's x times x? X squared, 0.26 minus x. Okay. So what we'll do now is something called the low ionization assumption. We'll assume this x that's moving in the forward direction is small. Okay, so assume x is small. So actually the threshold is 5%, but on the exam, it's going to be weak enough base, weak enough acid. It'll be less than 5%. Okay, so you can do this. This makes your life easier because number one, we don't have to do the quadratic. So now we have 4.4 times 10 to the minus 4 equals x squared divided by 0.26. This is called the low ionization assumption, and you can use this on the exam. No quadratic. So 4.4 times 10 to the minus 4 times 0.26. We'll square root that to give you x. And what is this on our calculator? Times 0.26. And where's the square root button on this guy? I'm getting 0.0107 big M. 0.0107 big M. Here you want to put the units. 0.0107 big M. Okay, this is X. But my question to you guys now, it's a very important question. Yes. What is X here? Really, what is X? Yes, okay, the X is this guy, but the X is also the OH minus hydroxide. So before we calculate the pH to get the answer, let's calculate the POH. Okay, let's calculate the POH. So the POH, as we know, or should remember, is minus the log of the OH minus concentration. So this is minus the log of 0.0107 big M. 0.0107, just leave the units. And minus the log of this. Minus log. I'm getting 1.97. That's not the answer. Okay, what is the answer? What's the pH? Okay, it's not 1.97, that's the POH. So how will we get the pH? pH plus POH is equal to what? 14. Power of acid in the form of H plus. Power of OH in the form of base, OH minus, is equal to 14. So what's 14 minus 1.97? 12.03. And this is the answer. Right, so this is the flow chart, okay, pipeline of how you want to do these types of problems. All right, and we assume it's less than 5% ionization, so you don't have to do quadratic. All right, so make sure you know that if it's an amine, it's a weak base. What other weak bases are there? The other weak bases are on page 17. Okay, so if you go to page 17, you don't have to memorize them, but I would say just recognize. Okay, recognize that these are weak bases. All right. So particularly the amines, ammonia. Okay, these are weak bases. All right.
You don't need to memorize them, just
Amines, weak base, you know, those types of things. Or, you know, if you see a KB, then you know it's a weak base. All right, just remember this here relationship. As your pH goes down, we're talking about the power of the hydrogen ion. That means it's more acidic. Okay. Other things also other things are also more acidic. Okay. That is, each acid has its Ka. So the higher the Ka, the lower the pKa. Okay. This also means more acidic. So just know that relationship. So on the test, you'll be asked to rank acids. Okay, I'll give you 5 acids. How will you know which acid is the most acidic? What do I mean by most acidic? You see, an acid is most acidic if it's really, really, really good at giving up protons. It's really, really good at protonating. I'm a strong acid. Really good acid. I protonate you guys, you there, all the way Lee at the back. That's a strong acid. How do I know which is stronger than the other, though? If I have 2 acids or 5 acids. Okay, you're going to search the one that has the what? Highest Ka or lowest pKa. Okay, the power of the Ka. Alright, so just letting you know on the quiz on the exam. Okay, I'll give you 5 acids. I'll give you the Ka, or I may be smart and give you the pKa. Okay, so what you want to do is compare evenly across the acids. Compare the pKa's. The lowest pKa will be the strongest acid. The highest pKa will be what? The weakest acid, so not very good at giving up protons, not very good at protonating. Or you put all the Ka's together, you know, on an array, or compare all the Ka's, and then you're looking for the highest Ka. Will be the strongest acid. The lowest Ka will be the weakest acid. Right? So we'll have a test review before the exam. We'll make sure we'll go over that again. Excuse me. Okay, page 18, let's compare some acids. All right, so which way does the equilibrium shift in the following reaction? We're on page 18 of our notes. Right or left? Equilibrium, okay. What do those arrows mean? The arrows mean an equilibrium. And here we have CH3COOH. This is called formic acid. This is called acetic acid, okay, like vinegar, acetic acid. Okay, here we have formate. Here, the CH3COO minus is called acetate. Okay, I'll give you these formula names. HCOOH is called formic acid. Okay, so you should be able to identify the conjugate acid and base pairs. If this is the acid, what is its conjugate? Acetate, right? If formate is the base, what is its conjugate acid? Formic acid. Okay? We see this a lot in chemistry, in organic chem, biochem. Acetic acid, acetate. Formate, formic acid. Ascorbic acid, vitamin C, ascorbate. Succinate, succinic acid. Okay, you see the differences? It's just the proton. One is the conjugate acid, the other is the conjugate base. So it's asking which one will this equilibrium favor? Will it have more to the right, or will it be more to the left? Here they tell us the pKa's. The pKa of acetic acid is 4.76. The pKa of formic acid is 3.75. Okay, so which is a stronger acid? Acetic acid or formic acid? Remember our trend. Okay, what are we supposed to know when we compare our acids? Okay, here we're given the pKa. So which is the strongest acid? Which is really good at protonating? Which is really good at donating its proton? Is it acetic or formic acid? It would be which one? Okay, why is formic acid the stronger acid, the better acid? Lower pKa, very good. Okay, low pKa, high Ka, lower pK, a better acid. So if this is the stronger acid, which way will the equilibrium shift? Which is better at protonating? Which is better at giving protons away? Yes. Okay, formic acid is better at giving off its proton. So formic acid is here, and it's better at giving off its proton. The equilibrium will shift to the left. Okay? So it's the stronger acid, better in donating its proton or protonating. So you're right, Maria, very nice. This is going to shift to the left, okay? Higher Ka, low pKa. This is the best acid. This is the best acid. All right, we did a weak base problem. Let's do a weak acid problem to round out this chapter. All right, the pH of 0.6 formic acid solution. The Ka of formic acid is 1.8 times 10 to the minus 4. So a question for you guys, what is formic acid? Is it a strong acid? Okay, the answer is no. Okay, is it a strong base? Okay, absolutely not, because first of all, the problem says acid. Okay, is it a weak base? No, because it's formic acid. Is it a weak acid? The answer is yes. Okay, it's a weak acid, and they even give you the Ka. Right, I'll give you the formula for formic acid. It's HCOOH. Okay, I'll give you that on the exam. All right, so once I give you the formula, once you can identify it as a weak acid, this is something you need to do, and that is write the formula, the reaction. So this is the reaction. Okay, what do weak acids do? They will react with water to give you what? Okay, they will react with water to give you H3O+. Plus the conjugate base. Right, so the Ka for this is something I'll give you, 1.8 times 10 to the minus 4. So also, can you guys tell me what's the conjugate acid and conjugate base pairs, the conjugates? Okay, formic acid, I'll give you the formula. Obviously, that's the acid. What is its conjugate base? Okay, HCOO minus. These are a couple. Okay, this is a couple. Okay, what is H2O here? Okay, it's the conjugate base. What is its conjugate acid? H3O plus. Okay, so this is a couple, and this is a couple. All right, back to the problem here. All right, don't worry about water. It's a liquid. Okay. So we have 0.6 molar. I have a bottle of formic acid. Okay. Formic acid. Does that bottle contain formic acid? Yes, but what else does it contain? Okay, it contains H3O plus and it contains HCOO minus. This is called formate. So we have 0.60. Initially this is 0. Some of it will react with water to go this way. So this would be minus X plus X plus X. 0.60 minus X plus X plus X. Okay. All right, just like we did with the weak base, we will plug it into our equilibrium. Okay, we'll be doing a lot of these in chapter 16. You'll be doing a lot of them in this 2-week lab, so split up your work accordingly. Make sure you know how to do it. Ka is equal to H3O plus HCOO minus divided by HCOOH. 1.8 times 10 to the minus 4. Okay, H3O plus is X, HCOO minus is X, X times X is X squared, divided by 0.60 minus X. Alright, just as we've done before, just like you'll do on the exam, we'll use the low ionization assumption. Okay, so there'll be no quadratic on this test. And this means 1.8 times 10 to the minus 4 is equal to X squared divided by 0.60. .8 times 10 to the minus 4 times 0.60 will square root this to give you X. And what is this on our calculator? Square root. 0.104 big M. Okay, 0.0104 big M. Alright. And what does that symbolize? It's X, but what does that X really mean? It's this X and this X. Okay? And one of those X's is H3O plus. And so now we can calculate the pH. pH is minus the log of H3O plus. Minus the log of 0.0104. And what did you guys get with that? Minus the log of 0.0104, about 1.98. Okay, so that's an acidic pH, and formic acid is an acid, so we would expect the pH to be below 7. Okay, so something like this on the exam, or the weak base problem on the exam. Right, so this is, like I said, the pipeline I want you to go through. Right, anybody have any comments or questions as we wrap up the last couple of pages of chapter 15? Okay, so this is what I want you to do, either if it's a weak acid or if it's a weak base. What if it's a strong acid? Okay, what will you do? Plug it into the pH. Okay, what are our strong acids?
Acid, nitric acid.
Very good. So here, no ice table, no, just plug it in. Plug it in, and plug it in. What is it? HCl, HNO3, H2SO4. What else? Chlorine is a halogen, hydrochloric acid. Bromine is a halogen, hydrobromic acid. Iodine is a halogen, hydroiodic acid. And then there's perchloric acid. Okay, so like I said, just plug it in straight to pH is minus the log of H plus. Okay, you'll do the same for a strong base, and that's anything that you see an OH minus in. Okay, so here you plug it in straight into the POH equation. The POH equation. Okay, our weak acid. Let's do this here. Okay, our weak acids are anything that's not this. Okay, and here I'll give you an example. We just went over formic acid and acetic acid. Okay, but there's a lot of weak acids. And here it's an ice table and low ionization assumption. Okay, weak source of H plus. Okay, this is strong source of H plus. Okay, plug it in. Okay, pH is minus the log of H plus. A strong OH minus source is OH minus. So this will really, really abstract that proton. So just plug it in, POH. And then the weak base, there is a page 17 has some weak bases. Okay, very classic example of a weak base is NH3, any of the amines. Okay, and we have a list here on page 17. This is what you have to do is an ice table. Okay, on the exam, you can use the low ionization assumption. This is a weak OH minus source. For your weak acids, okay, I'll have to give you the Ka, and for the weak bases, I have to give you the Kb. Okay. The Ka constant for the acid, or the Kb constant for the weak base. Alright, so this is kind of the summary of what we have done so far. And yeah. Right now I want to finish this thing up once and for all. We had a lot of disruptions. First we had the disruption of spring break, and then we had the test that sort of got jammed in the middle of all of this. So a little bit behind, but that's okay. We will get through it. So, yes, an equation here for you guys to know is Kw is equal to Ka times Kb. All right, at 25 degrees, Kw is 1.00 times 10 to the minus 14. All right, so what is Kw? Kw is in equilibrium. And what is that equilibrium reaction? Okay, the equilibrium reaction is for water. Okay, water. Okay, water donating a proton, another water molecule accepting that proton. So water protonating another water molecule. Right, so that's Kw. So this is a relationship that I want you guys to keep in the back of your mind. K's are quoted at a specific temperature, and this temperature for this constant is 25 degrees. All right, let's move on here. Polyprotic acids. All right, so a polyprotic acid, what does poly mean? Many, yes. So polyprotic acids give off many protons, okay? So we have one polyprotic acid that we talked about, and this is H2SO4. Remember this? So this is one of our strong acids, okay? Look at my arrows, okay? Everyone look at my arrows. Okay, because it's a strong acid, it's going to go to 100% ionization. And you'll get the conjugate base, HSO4 minus. Okay, but this is a strong acid. But what we have here is this molecule here, hydrogen sulfate, I think. This can donate a proton, okay? So H2SO4 can donate how many protons? 2, okay? It turns out the first one is very strong, very acidic. The first one goes. Okay, but this HSO4 minus can donate a proton to water. And look at my arrows here. In contrast. Okay, watch my arrow. Okay, this is sulfate, SO4 minus 2. So this is the common theme that we see in polyprotic acids. The first proton that comes off is very strong. That is to say, it comes off easy. What about the second? Okay, the second one is kind of weak. Okay, you see this hydrogen sulfate? This too can deliver a proton, but not as well. It doesn't deliver its proton well as the first one in the strong acid, sulfuric acid. We call sulfuric acid diprotic, okay, which means di means 2. Okay, so this has a Ka, and I'll call this Ka2 for the second proton in HSO4 minus. Here's something that's triprotic. What does tri mean? 3. Okay, so this is called phosphoric acid. Anybody here drink Coke? Okay, are you a big Coke fan? All right, so I used to drink a lot of Coke. My spouse says, "Oh, I wish you drank alcohol beer rather than all the Coke you drink." Okay, so you should drink alcohol instead of Coke, but I'm slowly getting rid of that habit. Why am I mentioning Coke? Because Coke has a lot of phosphoric acid. Have you ever watched YouTube videos where they'll clean a car battery with Coke? You didn't see this? Say it again.
That sounds very gross.
Yes. And there's also another one where they immerse or they soak an egg in Coke. And then I think a day or 2 or maybe 3 days, the egg becomes, you can remove the shell. Okay, it's like becomes hard boiled. That's the phosphoric acid. And then there's some that are even more gross where they clean like toilets and sinks and grime. Okay, it's the phosphoric acid. Okay, and it just happened. I know it. They put a lot of phosphoric acid in Coke. So phosphoric acid, since we're studying acids in this chapter, actually is triprotic. which means it can deliver not one, not two, but how many protons? This phosphoric acid can deliver up to 3 protons. Okay? So the first proton here reacts with water to give you the acid and dihydrogen phosphate. What do you think about this Ka value, 7.5 times 10 to the minus 3, pKa 2.12? Okay, pKa is minus the log of Ka. What do you think about this? Okay, it's kind of weak, okay, but do you see here the H2PO4 minus? What can it do? It can deliver a proton, okay? It can deliver a proton, give you acid, and give you HPO4 minus. Okay? And what do you think about that pKa? 63.21 corresponding to a Ka of 6.2 times 10 to the minus 4. Which is stronger? The first proton that comes off or the second? Okay, remember, lower the pKa, stronger the acid. So this would be a stronger, the first proton would be a stronger acid than the second one. But look at the HPO4 minus. What can it do? What can it do? It can donate its proton to give you acid, and you'll get inorganic phosphate. Inorganic phosphate, or phosphate. Tell me about this third pKa, 12.30. What do you guys think about that? Okay, it's pretty weak. Okay, why am I saying it's pretty weak? 4.8 times 10 to the minus 13, 10 to the minus 13, that is very small. Okay, 12.30, pKa is very high. So this is the common theme we see here. The first acid in a polyprotic acid tends to be acidic, or tends to go off strong. What about the second and third and subsequent protons? They get progressively weaker. Okay, they get progressively less acidic.
So like the last two, are those diprotic acids?
This is triprotic.
Oh, all three are triprotic?
Yeah. The substance, this molecule, is triprotic. Okay, phosphoric acid can deliver 1 proton and become this. This can deliver a second proton and become that, and this can deliver its third and final proton to become phosphate. Okay, but the point here, like any polyprotic acid, like H2SO4, like phosphoric acid, the first one is acidic, the second, third become less and less acidic. Subsequent protons become less and less acidic. The first one is pretty acidic, the second, third get less acidic. Okay, so this is the kind of the same thing that we are emphasizing above. To be honest, this is your take-home point. Okay, so this is enough for us to know now. Right, so let's go to the last 2 pages here. All right, let's go ahead and jump right into this problem here. Which of the following acids is weaker, HClO2 or HClO3? All right, so what's the difference between this acid and this acid? Okay, the difference between these 2 acids is that this one has 1 more oxygen. Okay, 1 more oxygen. So oxygen is an example of an atom that is electronegative. Okay, so what does electronegative? Okay, have you heard of a vacuum cleaner? Okay, what does a vacuum cleaner do? Okay, it pulls. Okay, it sucks dirt from wherever. Okay, so electronegative atoms, like the oxygen, are vacuum cleaners, and they pull and they suck out electron density. They pull. Okay, they pull on that bond. Oxygen, the halogens. Okay, they pull. So this oxygen 2 versus 3, there's more pulling power. So more pulling power means that it's going to pull, and this H will come off as H+. Okay, so that is what an electronegative atom will do. What are our electronegative atoms? Oxygen, nitrogen, all the halogens. They pull tremendously. Okay, so if I were to draw the structure of these, okay, they pull, they're pulling, and this chlorine is pulling and pulling. So eventually this H plus gets liberated. Okay, now we're adding a third oxygen. Okay, that's a lot of pulling. Okay, so more electronegative pull. Okay, the stronger the acid will be. So as you pull, okay, this chlorine is also pulling. This will come off. It will be liberated. Okay, it'll get liberated easier than something that just has 2 electronegative atoms. All right, so the weaker acid is going to be HClO2. Why? Okay, because it has less electronegative pull from the oxygens. This will be the stronger acid. Okay, more electronegative pull. By virtue of the oxygens. Okay, this will be the weaker acid. Okay, 3 oxygens versus 2 oxygens. Okay, the one with 3 oxygens or more electronegative atoms will be more acidic. Proton will come off easier. Okay, that's the take-home point.
So the weaker one is HCl2 because there's less electronegative pull?
Yes. Yes. That makes it a weaker acid. All right, so that's one take-home point. And then the final take-home point here is the last page. Okay. So this is something you can, just for your interest, I'm not going to really test you on it, but this whole chapter is on acids and bases. We know acids deliver protons, bases take protons. But how do you make these? Okay, how can you make an acid and a base? Okay, some of these you can just take from our lab. We have sodium oxide, dump it in water, and lo and behold, we have a strong base. So take some sodium oxide, dissolve it in water, you have OH minus strong base there. So that's how you make a strong base. How can you make an acid? Okay, if everybody inhales, exhales. As you exhale out some CO2. This CO2 will react with water to give you an acid. This is a weak acid, carbonic acid. Okay, this happens in our lungs. It also happens in our blood. So this is how you can make an acid, okay, just from a gas. All right. How can you make a strong acid? Okay, You take this gas, dinitrogen pentoxide, reacted with water, you get a strong acid. So there's many ways to make these, okay, from simple chemicals in a chemistry lab to gases. Okay, so I guess you should appreciate or realize that, gases can make strong acids, simple solids, oxides can make strong bases. Okay, this is the take-home point. Okay, your body does this reaction, okay, but it makes a weak acid. As this reaction also happens not only in the lung but in the blood. Okay, so anyways. All right, and finally, again, just for your own information, we've been talking about Brunstad acids and Brunstad bases. So what are Brunstad acids? They give H+, and this is an H+ taker. Okay, a giver and a taker. Okay, so this is the essence of chapter 15. But if you go to organic chemistry, how many of you take organic? Okay. All the majors will take organic chemistry. We have something called a Lewis acid and a Lewis base. This is not something I'm going to teach you, but a Lewis base will have spare electrons. Okay. So here in Brunstad acids and bases, which is the crux of chapter 15, we are transferring protons. Here we're transferring electrons. A Lewis base will have spare electrons, okay? And a Lewis acid will take those electrons. So here the transaction is with electrons. What we've been talking about in this class is the give and take of protons, all right? But if you take organic, there's something called Lewis acids and Lewis bases. Okay, so this is organic. This is what we'll focus on in the exam, the give and take of protons. Okay. And that concludes chapter 15. And now I have about 20 or so minutes. For the sake of getting us ahead, let's move on to chapter 16. Actually, just getting us on pace. All right, so chapter 15 is done. Make sure you turn in your homeworks, and I'll give you 10 points for that. All right, chapter 16, so 16, 17, and 18, and then we will be done. All right, so there's three main topics on chapter 16. Okay, the first topic is the common ion effect. Okay. The second topic is acid-base titrations. Okay, I'll also throw in buffers. And then the third main topic of this pretty heavy chapter is KSP. Okay, this is called the solubility product constant. All right, let's first talk about the common ion effect here. So we have here acetic acid. Okay, acetic acid reacts with water to give you H3O plus and acetate. Okay, and this is a weak acid, and it's going to have a Ka of about 1.75 times 10 to the minus 5. So 10 to the minus 5, that's a weak acid. All right, now imagine we take this acetic acid and we're going to dump some acetate into this. Okay, we're going to dump some sodium acetate. Okay, sodium acetate in water dissolves into its component ions, acetate ion and sodium ion. So if we take acetic acid, just a solution, and we take, I don't know, 1 gram, 2 grams, 10 grams, however much grams of sodium acetate, we dump it in here, you have a common ion. Okay, the common ion is acetate. So the common ion, what it will do, it will shift this equilibrium to the side that has less ions. Less ions. Which side has less ions? The reactant side. Okay? This side has the ion H3O+ and an ion acetate. The reactant side has no ions. So adding the common ion, this is just Le Chatelier's principle. It will suppress ionization. Okay, so this is the key point here. It's going to suppress ionization. This is what I want you to take home. Okay? Once you add a common ion, it will go to the side that has less ions. So suppression of ionization. So common ion effect, what will it do? Suppress ionization. So that's the key point here. Okay. Common ion effect suppresses ionization. Now I'm going to move on to page 2 here. Okay, suppresses ionization. That's what I want you to recognize. Okay, we'll go to the side that has less ions. All right, now I want to tell you something called KSP. Okay, KSP. I'm on page 2 now. All right, in this lab that you did last week, we had a solid called calcium iodate. Okay, this was a solid. I don't know if you remember last week's lab. This is a solid. Okay, see here a solid. This solid is actually in an equilibrium. This is called calcium iodate. This calcium iodate, it is a solid. You saw the solid. Okay, you split it up into 3 parts. Okay, can you remember last week? I know it's hard to remember yesterday. I'm asking to remember 7 days ago. You split it up into 3 parts. You kept 1 part in case something messed up. But it turns out this solid calcium iodate, you put it in 80 mils water. You put it in 40 mils water, 1 part. This calcium iodate will actually be in an equilibrium. It's a solid. It will be in equilibrium with its ions. Okay, the ion here is calcium, and then the iodate ion. Okay, we always balance our equations, and it will be 2 iodate. Okay, so here, this solid is in an equilibrium with its ions. So we have, anytime you have an equilibrium, which is this back and forth arrow, it does not go to 100%. It's either skewed this way or skewed that way. But anytime you have those back and forth arrows, you have a K. This is not Ka because this is not an acid. This is not Kb because this is not a base. Okay? This is not Kw because this is not water. Okay, what this is going to be KSP. Okay, and the KSP here is going to be concentration of products over reactants, but we never touch solids. So this is the KSP constant for calcium iodate. Okay, why did I put a square here? Why did I put a square here? Because of the coefficient, yes. So this KSP is a new K we're talking about, okay? And it's called the solubility product constant. Okay, so we will use the solubility product constant for sparingly soluble solids. That's another association linkage I want you to make. Common ion effect, suppress ionization. KSP, sparingly soluble solids. Okay, so I do not know what the KSP is. I could definitely look it up in the book or on the internet. But most of these solids are going to remain here. In fact, if you look on page, whatever it is in our notes, page something something, okay, you actually have a list of KSPs. And yeah, page 12, okay, page 12, okay. So we do not memorize these KSP constants, but these solids are in an equilibrium with their ions. Okay, sparingly soluble solids. So some of that calcium iodate, if you remember in the lab, will actually go this way and give you calcium ion and iodate ion. Okay, this is what we were trying to measure when you took that precipitate and put it in 80 mils water and 40 mils water, and you did the titrations. Okay, you're measuring, you know, how much the iodate reacts, and you're trying to, through the reaction, get a KSP. Right? But KSP is for sparingly soluble solids. What do you need here in the reactant side for a KSP? Solid. Okay, what will the solid go back to? It'll go back to its ions. Okay, here's another example. Calcium fluoride is a solid, but it's in an equilibrium with its ions, calcium ion and fluoride ion. Okay, so question here. Okay, so this will have a KSP.
So the calcium iodate, which way is it shifting?
We didn't add anything yet.
Oh, okay.
Okay, but this is the KSP for calcium fluoride, sparingly soluble solid. But let's say we add, I don't know, calcium nitrate. Calcium nitrate. Okay, let's say we add calcium nitrate to this solid. Let's say we add calcium nitrate to this calcium iodate. Okay, all nitrates are soluble. What happens if we add calcium nitrate to this? What happens if we add calcium nitrate to this calcium iodate? Okay, what do we have here? We have a common ion. What is our common ion? Calcium. So which way will the reaction shift? What does a common ion do? It suppresses what? Ionization. Okay, so if we add a source of calcium, calcium nitrate is dissolved in water. In fact, all nitrates dissolve in water. If we add a source of calcium ion, it's going to make more solid. Common ion suppresses ionization. It will shift the equilibrium away from the ions. Okay? If we add calcium nitrate to this solid, okay, what will it do? Remember, some of it is going this way. We add calcium nitrate, the common ion, will make more solid because the common ion suppresses ionization. So this is what I want you to know. The common ion suppresses ionization, whether it is a sparingly soluble solid or whether it's a Ka, acetic acid, whether it's KSP, or whether it's whatever it is. Okay, it's going to suppress ionization. All right, so that's the main point. We're introducing KSP. Okay, we have a solid going to its ions. Add a common ion. Suppression of ionization. I want you to just associate or link those concepts together. Okay, so here's an equation. I'll give you this equation on the exam. This is called the Henderson-Hasselbalch equation. So it's an interesting story with these two guys. Henderson and Hasselbalch were actually doctors at Harvard Medical School in the 1900s. So they were physiologists. And there's, I believe, there's something called Hasselbalch Hall in Harvard. Okay, so they're physiologists. They're measuring physiology. I never had a physiology class, so I couldn't tell you what all of that is. But they have an equation that's very, very famous. We use this a lot in Gen Chem, and we generally use it in the application of buffers. Okay, so first let me give you the equation. Okay, I used to derive it, but I'm not going to derive it anymore because nobody wants to see derivations. It's a different time now. Okay, but deriving it is very, very simple. But I'll just give you the equation, and I'll give this to you on the exam. Okay, pH is equal to pKa plus log. Now, if you're ever in a situation where, I don't know, you're stuck in an island and you need to know this equation, you don't have it memorized. Okay, pH equals pKa plus log. Okay, something you'll memorize. Okay, and if you don't know where goes what, okay, you can memorize a drop the acid. Drop the acid. Okay, that's what you know. The acid goes in the denominator, and the conjugate base goes in the numerator. Okay, so this is how you will get the pH of a buffer. I'll give you this equation on the exam, but if you're in a situation where you need the Henderson-Hasselbalch equation, okay, drop the acid. Drop the acid. HA goes down the denominator. All right, so pH equals pKa plus log of A minus divided by HA. Okay, we use it for buffers. So what is a buffer? Okay, so buffers are substances that withstand fluctuations in pH. I can tell you those substances that are composed of A minus and HA. It's a weak acid and its conjugate. Okay, so weak acid and its conjugate base, and they will withstand pH fluctuations. They make the pH stable. Okay. So you want your pH to be stable. Okay, we have something called buffering capacity. The best buffering capacity is where pH equals pKa plus minus 1. Okay, pH is equal to pKa plus minus 1. That is the best situation where it can withstand pH fluctuations. Okay, so it keeps the pH steady. That's what a buffer does. If you don't understand all of this, just it keeps the pH steady. So that's what a buffer is. We use a buffer. If we want to get a pH of a buffer, we will use this equation. We have a situation where if you have an A- acid conjugate with the acid, HA, if they have concentrations of those, you can plug it in here and get the pH. Remember what pKa is. Okay, minus the log of Ka. Okay, so remember pKa is the power of the Ka. So that's the important point that I want you guys to know here about buffers. Okay. Now, if I have a buffer, which is a conjugate acid with its conjugate base, okay, why are there no strong acids or no strong base in the buffer? Why will you never have strong acids or strong bases in a buffer? Remember, what is the job of a buffer? It's to keep the pH steady. Okay, if you add a strong acid in there, okay, your buffer can never have a strong acid. Why? Because it'll eat up all the base. Okay, so that's not how you construct or make a buffer. Okay, a buffer is always going to be weak acid with its weak conjugate base, or with its conjugate base. Okay. So let's say for an example we have acetic acid. Okay, the conjugate for acetic acid is acetate. It's 1043. Okay. So if you add a little HCl here, okay, which is a strong acid, it will get neutralized by this. Okay, if you add a little bit of OH here, okay, this will get neutralized by this because this strong base will react and take away this proton. This strong acid will protonate this. Okay, so this weak acid and weak conjugate base, WCB, weak conjugate base, can work to neutralize strong acid to strong base to some degree. But the minute you add a strong base as a component of your buffer, all bets are off. The game is over. Why? If you have an OH in your buffer, what will it do? It will eat up all of this. If your buffer contains HCl, what will it do? What will it do? If your buffer contains HCl, what will it do? It will eat up all the base. Okay, so the strong base will eat up all the acid. The strong acid will eat up all the base. That's not how you make a buffer. That's not how you keep the pH steady. Okay, the way you keep the pH steady is you make your buffer have a weak acid along with its conjugate base. So nothing strong in your buffer. Strong acids will lower the pH, will plummet it. Strong bases will increase the pH, increase it. Okay, that's not how you keep your pH steady. Okay, take home point, no strong acids, no strong bases. So how will you make a buffer? A weak acid with its weak conjugate. That's how you make a buffer. Right. All right. Now on Thursday we will, we'll finish this up, get as much as we can. We'll do some titrations on Thursday. All right, we'll start on page 3. All right, once again, there's no lab. All right, but work on your problems, get together with your lab group, turn in your homework so that I can put in your points. You can turn in the lab you did last week, you could turn it in next week. Right, so I pushed everything back. One more thing. This is important. This lab, you have a problem set. You can skip KF problems, complex ions. Okay, you can skip those. Okay, I'm not going to talk about complex ions, so don't do that. Okay, Yeah, you can omit it. Okay? If you want to do it, then check your answers, which is fine, but we will not do complex ion, so skip KF. I think that's all I have.